My second Kahoot of the day. This is going to be in my head all weekend long. I don't know how many people we have in here today, so I'll give you another minute or two. Who's still working on getting in? Are we all in? Still people working? Nobody wants to admit it if they're still working on it. I think we're in. I don't see anybody frantically clicking. There should be like 5 more of us, but we're missing some people too, so. I'm gonna give you 20 seconds if you're still working. Then I'm clicking the button. All right, let's just do it. So start. So here we go. 4 questions about membrane things. How will the membrane potential change if sodium is at a high extracellular concentration and you open a sodium channel? So sodium's at high concentration outside, low in. I'm in your way. Are we getting more positive, more negative? Going in. A little bit of a split. Okay, so deal is, and this is the one to get your brain working. There'll be some other ones that you can build off that. So we've got a cell. That's hard to see. We have sodium ions at high concentration outside and low concentration inside. So if we open a channel that allows sodium ions to go through, that's how I draw channels. That's like a cross section through a channel, so you're seeing the pore. Sodium ions will come into the interior of the cell, down their concentration gradient, because they're going from high concentration to low. And as they do so, they will add positive charges to the inside of this membrane. Right? And they'll kind of cluster along the inside of the membrane. And comparatively, there'll be some negative things that are outside here that'll kind of be on the other side of the membrane. We measure membrane potentials on the inside of a cell, though. So this is supposed to be straight. This is supposed to be like a little microelectrode. You literally just like take a little tiny tube of glass, you pull it out so it's a really fine tip, and you poke it inside the cell, and you sample the charge environment inside this cell compared to a ground. And so what we would find is that the inside of the cell is a little bit more positive than the outside of the cell. So it should be more positive, which a majority of people said, so that's good. All right, let's do the next one. Good job, Josh. How will membrane potential change if chloride is at high extracellular concentration and you open a chloride channel? There's a picture. People are going nuts. Or negative, yeah. So the difference here, in both cases we got ions entering cells, right, going from high concentration outside to low concentration inside. But in this case, it's a negatively charged ion, so it will be adding negative charges to the inside. So good. Looks like we're in good shape. Still Josh. All right, how will the membrane potential change if potassium is high intracellular concentration and you open a potassium channel? High intracellular. Ooh, big split. All right. Well, more people said more negative than otherwise. So deal on this one. Here's the cell. You've got positively charged potassium ions, but they're at high intracellular concentration versus outside. So we open channels. Potassium's going to move down its concentration gradient, which means it's going to leave. And if it's leaving, that means the outside of the membrane is going to get more positive. But the inside of the membrane, which is where we measure it, because we poke a microelectrode into the inside so we can actually sample from in here, the inside of the membrane is going to be more negative. So you would be making the memory potential along the inside of the surface of the membrane. That's always how we measure memory potential. So we make the inside of the membrane more negative. Okay? Looking good. Looking good. I got one more question. I don't remember what it was. Oh, yeah. In the prior scenarios, what will eventually stop ions from moving after the channel opens? Why eventually are those ions going to stop moving? This was the very end of last time lecture. Oh my goodness, we're all over. Nobody knows. All right. That's okay. Okay, so you might think that eventually you're going to run out of concentration gradient, right? So, and this is the most common answer here. So you might think that if you open sodium ions, they'll flow in and they'll keep flowing in until finally you'll have equal concentrations of sodium over here and here. And if that ever happened, that would ultimately cause the ions to stop flowing if you ever got that many sodium ions to come in. What happens, though, is that there's something that will happen before you ever get to that point. And what happens is that you have positively charged sodium ions leaving the extracellular space where there's negative charge and entering into this positively charged environment. And so eventually what will happen is you'll get so much positive charge in here, those are supposed to be pluses, you get so much positive charge inside these cells that the positive charge will start to repel the sodium ions. And so some of them will kind of come in, get in here, and then take a U-turn and go back out. And you'll get to that point, there will be a point at which the movement of sodium ions going down their concentration gradient is balanced by the movement of sodium ions going down their electrical gradient, so going from positive to negatively charged areas. And so at some point you'll get a nice, just drawing over top of this until it is a mess, at some point you'll get to an equilibrium. And in fact, we even talked about that because that memory potential, that difference in charge that is adequate to counter the concentration gradient is called an equilibrium potential. Bless you. Equilibrium. It's called an equilibrium. The equilibrium part is because we have reached an equilibrium where there's equal movement back and forth across the membrane. And it's a potential because it is that specific charge difference where the electrical gradient is big enough to counter the concentration gradient. In a typical neuron, well, I shouldn't show this for sodium. Yeah, no, I'll do this. Okay, yeah, this is fine. So in a typical neuron, when you're dealing with sodium, a typical equilibrium potential might be something like plus 60 millivolts. So it's a positively charged number because that is reflecting the fact that in order to balance this concentration gradient where sodium's trying to come in, you need a pretty good amount of positive charges on the inside of the membrane. And about positive 60 millivolts is a typical-ish kind of a number. It'll vary from neuron to neuron. In fact, we're going to calculate that in a second. But does this make sense before we get into, why we're hitting this equilibrium? Right.
Sorry.
Yeah.
Why couldn't it be both red and
So it would be closure of the channel would mean that this channel is actually closing and no longer letting. Yeah. I mean, if the channel could close, I guess that could be a reason it could happen. Scandal. I didn't tell you the channel is gated though. Like I should have said it's a not gated channel, I guess. But this is what we talked about last time. This stuff. So, all right. Okay. All right. So give yourselves 300 Kahoot points, and then we'll. Yeah. No, I mean it's finals or whatever they are. But. All right. Okay, so there we go. So good job, TK. But if you must, you may add 300 Kahoot points. Okay. So let's get back to that point. So what we just did through that Kahoot quiz is we basically took a situation where we knew what the concentration gradient was, at least conceptually, and we knew the charge of the ion, and we were able to figure out at least what charge the equilibrium potential should be. Should it be a positive charge or a negative charge that would need to oppose the concentration gradient? So you have an equilibrium potential. We can do better than just predicting it, that sodium's equilibrium potential should be positive. We can actually predict the actual number of it, and we do so using this equation. It's called the Nernst equation. So the Nernst equation's job is to actually quantify and establish what is the equilibrium potential, what is that memory potential that would need to balance the concentration gradient for a specific ion. So again, here's a definition of the equilibrium potential. It's I guess it's not a definition. The equilibrium potential is that memory potential that would balance the concentration gradient for any given ion. It's going to be determined then by whatever that concentration gradient has to be. So if the concentration of sodium is higher outside a cell than inside, that will have a different equilibrium potential than if the concentration gradient were reversed, such that sodium was high inside cells. Okay, so it'll be determined by the concentration gradient for the ion involved and the charge of whatever the ion is. So sodium had a different we had a different answer for sodium than we did chloride, because they're both entering cells in our Kahoot quiz. One was positively charged, the other one was negatively charged. So a larger concentration gradient is going to require a larger equilibrium potential to oppose it in order to get to an equilibrium point. There's basically more push from the concentration gradient, so we need more push from the electrical gradient. And again, different charges on ions, positive versus negative, will generate different electrical potentials. So here is this beast that we've been talking about, and I've been sort of hinting at. It's called the Nernst equation. So it just reads the equilibrium potential of the ions, that's E ion, the equilibrium potential of an ion is going to be determined by a constant, which is at 37 degrees, it is 61.54 millivolts. We will always, always, always in this class deal with 37 degrees. It's always going to be 61.54 millivolts. That's just a constant. Okay, it makes the math work. Z, so it's 61.54 millivolts divided by Z, which is the charge of the ion. So if it was sodium, it would be +1, which is nice and convenient. But if it's chloride, it'd be a -1. If it was calcium, it would be +2. So that's just the charge, times the logarithm of the concentration of that ion outside of cells divided by the concentration of the ion inside of cells. Okay? In fact, I'm going to rewrite it because I'm going to ask you to try a calculation. I hope you can see it from here. So if you've got a calculator, time to pull it out. If you don't, your phone has one, probably, if you've got your phone. Your parents, I took my daughter's phone away for today, so if she was here, she was bad. So she said disrespectful things. So here we are, 61.54 millivolts. So here, let me hang on. So what we need to do is I need to give you some actual values. I would like you to try to calculate the equilibrium potentials for these ions at these concentrations. So I'm giving you the ions, so you can get the charge from that. I'm giving you the concentration outside of cell and the concentration inside of cell. And your job is going to be to try to work through how to do this. I'm going to give you a second to play with it, and then I'm going to type it out on my calculator and show you how I have to do it. I have two different calculators. I forgot one. But one of them works one way, the other one works another way. See if you can get these. because so these cancel. This would be lingering. You know what I'm going to do? Let's pull up my computer calculator here. Let me walk you through this one, and then I'll turn you back loose to keep working on the next ones. So the first thing I like to do, I am a methodical, this is another point of contention between my daughter and I, but it's unrelated. I'm a methodical math person. So I like to first plug in numbers to my equation, and if we had to solve the equation, I'd do that first too. But so here I've got, here's the original equation. Here is 61.54 divided by Z for potassium ions, that'd be a +1, right? Times the logarithm of 5 millimolar divided by 100 millimolar. Units would cancel on the millimolars, so these cancel away. So you don't have to worry about them anymore. They go away. That one's still there. And then if I'm going to do this on a lot of calculators, this is the way, I think this is the way my Android one does. It's definitely the way my iPhone calculator used to work. It's also the way the one that comes on Windows works. I think, well, hang on, is that right? No. Yep. So what I have to do is kind of do this problem backwards. I go 5 divided by 100. I have to start with what's in the parentheses. 5 divided by 100 equals 0.05. So I rewrite the whole thing again. That's what I do. And then once I figure this out, then I hit, I have 0.05. I hit the log button, so I take the logarithm of it. Boop. So that's done. So if you wanted, you could even rewrite it again. It would be 61.54 divided by 1 times minus 1.3. But now, if I just take minus 1.3, and then I multiply by 61.54, and then because I'm OCD, I divide by 1, which we all know what was going to happen if you divide by 1, but I just do it anyway. I get minus 80 millivolts. I think most of the time you can just round to the nearest millivolt and you're fine. Sorry, I'm getting beeped. Okay. Is that okay? Everybody still struggling? You may have a fancy pants calculator. So I have another nice handheld calculator that's sitting in my office where I would just type in 61.54 millivolts divided by 1 times, and then I hit the log button and it opens some parentheses for me, and I can type 5 divided by 100, and I close the parentheses and I hit enter, and it does the whole thing at once. But most of the time, if I'm using my phone or if I'm using the computer calculator, I have to do it this sort of backwards way, where I do what's in the parentheses first, hit enter, hit the log button, and then multiply by the first part. Is that okay? Yeah. Not really. I think it's good to show your work, but I mean, if you get it right, that's fine. I do think I would recommend at least writing out the equation before you plug it into your calculator, at least. See if you can get the next 3. We'll go from there. Yeah, I think nearest millivolt's good. I try to be sensitive to rounding errors. another minute or so, and then we'll just start having people call them out. And then if you need to get caught up, you can always do these again later. Okay, so who's got a equilibrium potential for sodium that you calculated? Plus 61 point. I'm gonna say plus 62, but okay. 61.54, 62. Is that what everybody else got? Anybody have a different number? I can get a lot of shaking head, yes. So that sounds good, and that looks about right to me. I didn't bring a cheat sheet. Calcium. Anybody get calcium? 123, is that what you said? So I'm going to put a plus there just to be clear about it, but okay. What about chloride? What'd you get? I'm hearing minus 65. Sound good? Yeah, so you can calculate these. So we calculate, I'm going to come back to potassium. So what does that mean that we calculated potassium's equilibrium potential to be minus 80 millivolts? Like what is, we can do that math, that's good, but what is that telling us? I don't think anybody's going to want to step out of them and try to answer that. So, I mean, one thing I'll point out, right, is that here's this sketch we did of potassium earlier, right, during our Kahoot quiz. And we said potassium was at high concentration inside and low concentration outside. And I did give you numbers that had high concentration potassium inside and low outside. This is because of the sodium potassium pump, because it pumps potassium in. So we tend to have a high concentration inside cells. And so we said that the membrane, this would cause the membrane to change its membrane potential to become more negative. And eventually it would probably stop when we get so negative inside and therefore so positive outside that potassium ions start to stream back into this cell down their electrical gradient, right? So at some point, if you get enough negativeness inside, these positively charged potassium ions will start flowing back in, and there'll be a point at which we'll equalize. We'll hit an equilibrium where the rate at which potassium ions diffuse out as they go down their concentration gradient will equal the rate at which they diffuse in down their electrical gradient. The specific membrane potential value at which that would happen is what we just calculated. This would be at minus 80 millivolts. We will hit that equilibrium. This is our equilibrium potential. Okay? So that's what it actually is telling us. This is basically telling us that there's another way I can tell you this too. This is also kind of saying that potassium ions will move and cause the membrane to change and shift toward this minus 80 millivolt value, because they will flow. As long as we're not at minus 80 millivolts, we'll have a net movement of potassium ions, and they will push the membrane potential towards minus 80 millivolts. So there's a way in which the effects of potassium is basically to try to shift the membrane potential of this cell towards minus 80 millivolts. It shifts toward its equilibrium potential. That's kind of nice. For sodium, we said the membrane potential should get more positive, right? Because sodium ions are rushing in, they make the inside more positive until we hit an equilibrium. The point at which we hit that equilibrium would be plus 62 millivolts. That's nice and consistent. Chloride, we said, would be a negative number in the Kahoot quiz, and here we calculated minus 65 millivolts. We didn't do for calcium, but calcium is kind of the same thing as sodium, right? I mean, it was higher outside than inside, just like sodium was. The only difference is it's a plus 2 and so its charge kind of like counts for more, but it's going to shift in the same direction. But again, we can quantify exactly how it would work with this Nernst equation. So this is telling us not only what is the point at which these ions won't flow across the membrane anymore, it also, like I'm sort of saying, it kind of tells you what that ion does to the memory potential. Because if the ion is not at its equilibrium potential, it's going to flow and shift the memory potential towards that equilibrium potential. I'll do more on that in a sec here. Okay. So I think we said these things. So I asked, what are you calculating? What does that mean? The sign of the equilibrium potential that we calculated should match what we predicted on the Kahoot quiz, and we talked about that as well. A few additional points before we'll keep going and try to get to real neurons in a second here. But along these points about ions shifting memory potentials, it actually turns out that certainly there are ions flowing. So we would say that the moment ions start to move across the membrane, that's going to change the concentration of that ion from one side of the membrane to the other. It turns out that if you actually measure this, though, the amount of concentration difference, basically the number of ions that flow across the membrane, really doesn't have to be very many before you get a big difference in memory potential. So we will go from a point where maybe we're at a neutral memory potential to, if we opened a bunch of potassium ions, like in this case, we would get to this point where we're at our equilibrium really quickly. So what your book reports is that you might shift from 100 millimolar potassium concentration to maybe 99.999999 millimolar in order to move the memory potential from 0 millivolts all the way down to minus 80 millivolts. So while, yes, ions are moving across the membrane, it's almost a negligible amount from the standpoint of looking at concentrations. So when we start to talk about how neurons work, we're really never changing our concentration gradients at all. The concentration gradients are established by the sodium-potassium pump, but then they just kind of stick and stay exactly where they are. So we're not going to really change the concentration gradient. What will change is how rapidly different ions are moving across membranes. And that's what really causes any kind of change in memory potential. So you can treat concentrations as effectively unmovable sorts of entities. The charged particles, I think I mentioned this last time, but the charged particles really only cluster along the inside of that membrane. So it's not like as potassium ion starts to stream out of the cell that the whole inside of the cell becomes negative. Really what happens is there's just like this band of negative charges right along the inside of the membrane, a band of positive charges right across it, and they're attracted like little magnets across that membrane. But the whole, like the charge properties of the entire solution don't really change. It's just right along that membrane. And then the final thing I'd like to point out is that ions will move faster as the difference between your membrane potential, this is whatever the current membrane potential is, as that membrane potential, the bigger the difference between your membrane potential currently and whatever the equilibrium potential is of your ion, as that difference gets bigger, the ions move faster. So sometimes this is referred to as the ionic driving force. So what this is saying is that if I'm starting at 0 and the equilibrium potential of potassium is minus 80, lots of potassium ions are going to start streaming across this membrane. If I start at minus 79 millivolts, though, and the equilibrium potential of potassium is minus 80, I'm almost there. And so you won't get a whole lot of ions moving across at that point. Maybe a few initially, but you won't get very many moving across. So again, that difference between your current memory potential and the equilibrium potential of an ion is called the ionic driving force. And we'll see that again later. That's why I'm sort of bringing it up now. So how are we feeling? Is that kind of okay? I mean, it can be okay. It's fine if it's not entirely okay in your head. It's just the kind of okay is good. And then you can go back over stuff. So what we've been talking about, these are kind of artificial situations, right? So we're talking about a cell that kind of, usually these cells, there's no other ion involved in these scenarios. We're starting from scratch, and then we open a channel that only lets one ion through. What we want to do now is try to understand what's going on in real cells, where there's more than one ion that can be present. So the actual memory potential of a cell, it will be affected by whatever ions are coming across it. So basically, any ion that's permeable is going to be affecting the memory potential of a cell. And the more permeable ions are, the larger effect they tend to have on the membrane potential. So, for example, in neurons, in most neurons, there is a very high permeability to potassium, pretty much all the time. There's lots of channels for potassium that are just always open. We call them potassium leak channels. And so as a result, potassium usually has a big say in the membrane potential of a neuron. The same is not true for calcium or chloride, and is only occasionally true for sodium. But potassium, it always tends to be important. So if we imagine a neuron in which only one ion, let's say only potassium, is permeable, then ions are basically just going to do what they did in our thought experiment here. They're going to flow such that the membrane will shift from the equilibrium potential, shift from the current membrane potential to the equilibrium potential. So this is what we did before. If we started with a situation where there was high concentration of potassium inside, and then we open a channel, potassium ions will flow out, make the outside of the membrane more positive, the inside becomes more negative, and the ions will continue to flow out until such time that the concentration gradient is balanced by this electrical gradient, and that's the equilibrium potential. So we will, by opening a channel for potassium, we can cause the membrane potential of our cell to move to the equilibrium potential of potassium. It'll go to -80, and at that point then we'll kind of hit an equilibrium. In neurons, though, we don't just have one ion, so maybe we also have sodium involved. Sodium, as we did over here, kind of works in the opposite direction because usually the concentration gradient is different. So if we had a neuron that only had permeability to sodium, and we open a bunch of sodium channels, sodium ions would rush in, just like we did here, until such time that the inside of the membrane got so positive that sodium ions were being repelled out down their electrical gradient at the same rate they were coming in via the concentration gradient. Now, in a real cell, we would have both sodium and potassium channels open at the same time, oftentimes. So if that's true, if sodium and potassium channels are both open, we know what they're doing by themselves. So by themselves, potassium pushes the membrane potential to -80. By itself, sodium ions push the membrane potential to +62. If you had both kinds of channels open, where do you think we're going to be? What's that neuron's membrane potential going to be if it's got sodium and potassium ions flowing across? What do you think? Any ideas? Let's get one more time. So only potassium by itself, the membrane potential shifts to -80. If it was only sodium ions able to get across by themselves, membrane potential shifts to +62. So what do you think, where would we be? You don't have to give me like a specific number, but like where might we be if both potassium and sodium ions can both get across this membrane? What do you think? And why slightly negative? Yeah, so you're kind of like splitting the difference, right? So like somewhere in between, right? I think that would be what we'd expect, like somewhere in between. If we're dead on having like between these two, then I guess we'd be a little minus because potassium pushes you to -80, sodium only pushes you to +62, so maybe you're at like -10. So but I think the point is that not so much that it'd be negative. The point is that it'd be somewhere intermediate between these, and maybe we don't know exactly where it would be yet. But somewhere in between these is where we should be. What do you think would happen if the membrane potential is 40 times more permeable to potassium than sodium? So sodium is still permeable, but you are 40 times more permeable to potassium than sodium. Like where are we roughly going to be? Are we going to be around 0? Are we going to be close to -80? Close to +62? Like what do you think? Yeah, we should be close to potassium, right? So like potassium is really permeable. There's lots of channels for potassium. It can stream across pretty easily. There's only a few channels for sodium. So most of the effect, like potassium should kind of win here. And most of the membrane potential should basically be pushed almost to -80. But you might not get all the way to -80 because there still are sodium ions that are going to be creeping across through their limited permeability, and they're going to be pushing the membrane potential the other way. So you can think of these ions as kind of fighting over what the membrane potential will be. And in this case, because potassium is so much more permeable to sodium, potassium should be driving the effect. You should be mostly pushing towards the equilibrium potential of potassium. But that's not to say sodium has no effect. It probably still will matter at least a little bit. This is honestly, this is the way most neurons are at rest. So at rest, a typical neuron, so when there's no action potentials, a typical neuron will have very high permeability to potassium, about 40 times the permeability of potassium as sodium. So the memory potential will tend to be pretty close to -80. And that's a pretty typical value for a normal neuron. Does that make sense, more or less? So the great thing is, we don't really have to just kind of eyeball it and say, well, it's kind of halfway would be about -10-ish, or here we should be close to -80. We can actually quantify this, and that's where this the second equation comes in. So we can make quantitative predictions of memory potentials in situations in membranes where we have more than one permeable ion. And the way we do that is with this equation. It's called the Goldman equation, which looks a little scary, but it's not really that bad. In fact, it's pretty darn similar to the Nernst equation. So let me walk you through it. So it's saying that the memory potential, so this is the actual memory potential of a cell. We're not calculating equilibrium potentials anymore. We're calculating the actual memory potential of a neuron, will be equal to 61.54 millivolts. That's that same constant we saw before. We're not worrying about charge because we're dealing with more than one ion. So it's 61.54 millivolts times the logarithm of this big thing. This big thing is saying has pKs and concentrations in it. So pK means the relative permeability to potassium. So this is just a unit number. So this could be a 1, this could be a 5, this could be a 10, whatever it happens to be. This is telling you how permeable you are to potassium. So when I said that potassium's permeability in a typical neuron is 40 times that of sodium, you might plug a 40 in here for potassium. PNA is over here. This is the permeability of sodium. So if potassium is 40 times as permeable as sodium, the potassium permeability might be 40, sodium's permeability might be 1. Okay? So that would mean that you're 40 times as permeable to potassium as sodium. And it's a relative number. They're all relative to each other. This is permeability to chloride. If we want to bring chloride into it, we don't have to. It sort of depends on how we plug it in. So anyway, for each of these permeabilities, what you do is you take the permeability of potassium times the concentration of ions, potassium ions outside the cell. That's the O. And then to that, you add the permeability of sodium times the concentration of sodium ions outside the cell. And then to that, you add the permeability of chloride times the concentration of chloride ions inside the cell. See, there's an inside there instead of an out. You add all these together. And then you take all of them divided by this whole thing, which would be permeability of potassium times potassium inside, permeability of sodium times sodium inside, permeability of chloride times chloride outside. So you have to do all of this on top first, all of this on bottom, and then divide this whole value by this whole value. That's the way the math works. Okay? Yeah, I was about to ask you guys that, why you think that is. And that's right. So the reason, so these guys up here, that you go out concentration of out over the concentration inside. That is right what we did with the Nernst equation. Out was divided by in. But with chloride ions, it's in divided by out. And that is because we don't have another way to get the charge in that equation. So we just flip them and it works. We could walk through the math if you want. It's because it's a logarithm that works. Okay. So it looks kind of ugly, but again, I mean, it's just pretty basic algebra. Just take your time through it. You got to multiply your permeability times your concentration here and add that to this permeability times concentration. So you work your way through the whole top numerator, work your way through the whole denominator, divide one by the other, then hit the log button, and then multiply by 61.54. It takes a while. It's tedious. I know it is tedious. Once you're able to do it comfortably on a calculator, if you want to do it in Excel or something to speed it up, you can. That's fine. But the great thing about all this is that this equation will give us pretty accurate estimates of the memory potential of any given neuron if we know how permeable all the different ions are and if we know the concentrations of all those different ions. There's this little question that's kind of cool. So what would happen to this equation if only one ion was permeable? So if the permeability of, let's say, potassium was 1, but the permeability of sodium and chloride were both 0. You see what happens to the equation? It's like if that number, permeability to sodium, is 0, so no sodium ions can get across, this whole thing becomes 0, right? So we're adding 0. If permeable chloride is 0, that becomes 0. This is 0. This is 0. And the only thing that would be left would be the ions that are permeable. So now we're at 61.54 times logarithm of the permeability potassium times concentration out, permeability potassium times concentration in. The permeabilities would cancel at that point, and we're left with this equation. I mean, it reduces down to the Nernst equation if only one ion can get across. You see that? Kind of neat. So they're all derived from each other. Okay, so let's try it. Think of it as fun. So what I'd like you to do is, so here are ion concentrations. These are the same concentrations from the prior calculations we were doing. And then here are some relative permeabilities. I'm saying that the permeability of potassium is 40 times that of sodium. So I got a 40 for potassium. I got just a 1 for sodium. And I'm going to give you initially, let's just say that the chloride permeability is 0. So you could just ignore that part and just do sodium and potassium. I need more whiteboard. I'm going to plug while you chug. What are you doing? Do that right? There it is. So I haven't quite gotten to the end here, but we're running out of time. So this is what I did. So I plugged in all my values here. And then what I like to do is just, again, I'm going to do the top row first, and then I'll do the bottom row, get them here. So this would end up being 350 divided by 4015. And then you hit the log button on that, and you hit this, and what do we get for our overall value? Anybody get the end? Sweet. That sounds right. So here's the thing. This is cool, right? Look at what happens because of these permeabilities. You see how this number, like the overall value, how this thing really, this is like dominating, right? It's dominating the effect. And this is because potassium has high concentration inside and high permeability. And that part, that number right there is kind of dominating everything else. So it's the permeability of potassium here that's allowing potassium to dominate. All right, so I'd like you to give that a shot. You can do these on your own, but you can also, on the homework, there are a whole set that you can work on the homework. So I'd like you to give it a shot for Monday. Do your best. We'll see where we get. I feel like we're in a good spot, but if you're really struggling, send me emails. I might be able to help. Yeah. Oh, gosh. I mean, it's probably rounding. If you rounded that, if you rounded that, and that, I'm sure, is what it is.
Right, it just makes sense.
So if you added like 3 or 4 more digits to it, and then you'd be fine.
Okay, so for these,
Yeah.
to be able to know which way you draw the arrows, like what is like our reference point?
You need to know the concentrations. And they're up here. So
Okay,
using
so we're
these
just-
concentrations.
Compared to this.
Yes.
Okay.
Yep. 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 You should be good.